Chapter 6, Section 6.1, Verifying Trigonometric Identities. We have one major objective in this section, using trigonometric identities to verify a given identity. If you like algebra and arithmetic, this is your thing. We're going to use these fundamental identities that have been developed over the course to prove equations that aren't yet equations until they are proven. In other words, these are identities where the left and right side will be equivalent, and we have to show that they are equivalent, and then it is an equation because both sides will be equal to one another. And these are some of the pieces that we will use in order to get the job done. Okay, how is it will we do this? So we're going to refer to this box again and again as we move forward. To verify identities, we show that one side of the identity can be simplified so that it is identical to the other side. And this part here is very important. Each side of the equation is manipulated independently of the other side of the equation. You cannot cross over the equal sign. If you do, that assumes it's already balanced, meaning equal, and your set task is to show that it's equal. Start with one side containing the more complicated expression. If you substitute one or more of the fundamental identities on the more complicated side, you will often be able to rewrite it in a form identical to that of the other side. So there's two ways to proceed. Work left side only until you end up with the right side, or equivalently, start on the right side and manipulate until you end up with the left, or you are allowed to work both sides independently of one another until you've reached equality on both sides. We have one major problem to do here in the PowerPoint slide. It's rather complicated, so what I'll do is instead move to the problem areas, and I'll work some basic problems to show you how this is done, and we'll keep this list up here for reference as much as we can. So let's work the first problem right here. Verify that this identity is true. So the identity here that we have is, show that the cosecant of x multiplied by the tangent of x function will be equal to the secant of x. Okay, what I'd like to do is put a line right down through here. This is a wall to remind me that I cannot move across the wall. Either manipulate this until you get secant x, much more difficult, manipulate the right side until you get cosecant times tangent, or work both sides independently until you get equality. This one's quite basic. Okay, cosecant. Do we have a fundamental identity for cosecant? So we'll appeal up here to our basic identity list here, and we see from here the cosecant. Here's the cosecant, can be represented by 1 over sine. They are equal. This in itself is an identity. We don't need to prove it. We are given this as the fundamental starting blocks and the fundamental pieces of the puzzle. So let's replace cosecant with 1 over sine. So right here we've got cosecant. That's the same thing as 1 over the sine. Then we got times tangent x. Well, let's see, tangent x here is sine x divided by cosine x. So we can replace tangent x anytime we want with sine of x over cosine of x. Okay, having done that, we now have two fractions that we can push together with multiplication. 1 times sine of x is the sine of x, and sine of x times cosine x, we'll just write that down as a product, sine x times cos x. Because we have multiplication, and only because it's multiplication, we can divide numerator and denominator by sine of x, and that gives us 1 over the cosine of x. Okay, well, 1 over the cosine of x, go back to our fundamental identities here, 1 divided by cosine of x, here it is, is equal to the secant of x. So we can replace 1 over cosine with secant of x. So what we have is we started on the left side, we stayed on the left side, and we have ended up with what's on the right side. So we have indeed shown that the left side can be transformed into the right side. Now we know that this is equal. Okay, so there's the first one. Let's do another one. Verify the identity number 2. Let's turn the paper like this. Verify the identity that cosine of x times the cotangent of x plus the sine of x show that when manipulated can result in simply being the cosecant of x function. Okay. Cosine times the cotangent plus the sine equals the cosecant. Okay. You saw in a previous problem that one strategy is to convert everything to sines and cosines. So this one's already cosine, so let's leave it alone. Times the cotangent. Okay, so by our fundamental list of identities here, the cotangent, okay, well, the cotangent's 1 over the tangent, and the cotangent's also cosine over sine. Let's choose this one because our strategy at this point seems to be reduce everything down to sines and cosines. So let's do that. Cotangent is the cosine divided by the sine. Okay. Add to that the sine of x. Okay, so we've transformed everything on the left side to just cosines and sines. So this is a fraction here, over 1. Let's multiply top and bottoms. So that gives us cosine square x over sine of x plus sine of x. Now what? It's difficult to know sometimes what to do, and there are multiple ways that this can be done, and you have to have good arithmetic and algebra skill to get this done, and it takes a lot of doing before you see how it works. It's like putting together puzzles or playing chess. There is a strategy that's not necessarily obvious, and the rules here of the game are very simple. Well, let's see. We have this is a fraction as well. Why don't we add that fraction together and find a common denominator? So this is cosine square x over sine of x. And this one we can multiply by the sine of x over the sine of x. So that will give us the sine square over the sine. Okay, so I'm taking this one and I'm multiplying by sine x over sine x. That way we have a common denominator down here. That means we can write that as a single fraction. Cosine square x plus sine square x divided by your common denominator of sine x. Okay, gets us that far. Now, one of your basic fundamental identities is that Pythagorean sine square plus cosine square is equal to 1. So we can, at any time, replace cosine square plus sine square with 1. 1 divided by the sine of x. Well, again, going back to our fundamental identities, 1 divided by the sine of x is the cosecant of x. So this is now the cosecant of x. So we have started with the left side here, and we have to end up with cosecant x, which we have done. So we have proven that identity is true. Okay, let's see what else we got. Problem 3. Verify this identity. Okay, sine of x minus sine of x times cosine square, sine of x times cosine square of x, show that that's equal to the sine of x all cubed. Okay. Again, there is more than one way to do this. In fact, many ways to do this. And from my experience, I could see how to show the right side's equal to the left, or that the left is equal to the right. It also depends upon what you know and what your skills are. So your point of attack might be different from person to person or problem to problem. Typically, you start with the more complex side, which appears to be the left side. So if I do that, what is it I can do? Well, okay, you have a Pythagorean identity. Let me slide this over just a little bit here. You have a Pythagorean identity. Sine square x plus cosine square x is equal to 1. But we can rewrite that in one of two different ways. You can write sine square x is 1 minus cosine square x. That's a different way to write the top identity. Or you could rewrite this as cosine square x is 1 minus sine square x. So from one basic identity, we can manipulate it algebraically and represent two different identities in place of it. Okay, is any of that going to help me over here? Okay, I see two terms, and both terms contain a common factor of sine of x. I'm going to factor out sine of x because I see something. I see what would happen. This is not the only move. One move might be replace cosine square here with 1 minus sine square. And that would be a different way to proceed. And perhaps that would work, and perhaps you should try that. I'm saying if I factor out sine of x, I'm left with 1 minus cosine square. That's why I'm making this move. And I made that move because over here, 1 minus cosine square x is equal to sine square. So I can then come over here and replace 1 minus cosine square with sine square. And multiplying sine times sine square gives us sine cubed, and that's exactly what we needed to show. So we got it right there. Interesting to see if it would work by replacing this cosine square by 1 minus sine square. Maybe we should take a moment and just try that and see what happens. So let's take the original, sine x minus sine x times, and second attempt here, right? This is what's happening. Second attempt. Different way to think about it. Cosine square is given by, here it is, 1 minus sine square. So let's try to replace that. 1 minus sine square x. Okay, now what? Maybe we can distribute here. So we've got sine of x. Careful, the minus sign goes with it. Minus sine x times 1 is minus sine of x. Negative sine x times negative, well that's positive. Sine x times sine square would be sine cubed x. Look at that. Those two add up to be 0. So all that's remaining is sine cubed x, and we got it. So that seemed to be just as easy, but done by a different method. That's what I mean. These take practice, and there's a lot of various ways to do it. Some moves are arithmetic-based. Some moves are algebraic-based. Sometimes you have to rearrange a given identity and use it. It's a combination of a lot of different skills. These are frustrating and often take a lot of time. Okay, here we have one. I'm looking at number 4. Here it is. Let's try to verify that identity. So let's turn the paper like that. Verify that 1 plus cosine theta over sine theta is equal to secant theta plus cotangent theta. Okay, well, sometimes they use x for the variable, and sometimes they use theta. It could be y. The variable doesn't matter here. There's no trigonometry with right triangles or unit circles. So as long as there's a variable present, because sine just by itself is an abbreviation for sine, you need to take the sign of something for it to be a function. So as long as you have a variable, that's fine. Okay, well, we could, let's see, what could we do here? Let's think. If we start on the left side, our method of reducing to sines and cosines is already accomplished. Everything already is sine and cosine. So what further could be done? Well, we have a fraction here and a sum in the top. So just like in the numerical case where you have 2 plus 7 over 5, you could separate that to be 2 over 5 plus 2 over 7. Normally you think this way. I'm sorry, that's a 5 right there. Whoops. Let's do that again. 2 plus 7 over 5 is 2 over 5 plus 7 over 5. Okay. Normally you think this way, which is common denominator added together. But what goes one way also can go the other direction. And then this way is to separate. So this is separate, and this is combine. So knowing that we can do that, let's try to apply that over here. Let's separate 1 over sine theta plus cosine theta over sine theta. Now maybe this doesn't work. Not all things work. There are dead ends. In this case, 1 over sine theta by our basic formula sheet is secant theta, and cosine theta divided by sine theta is indeed cotangent theta, and we got it right away. We have started with the left and ended up with the right. Now another way to attack it is, let's suppose we start with the right side. Okay, there it is. And I want to end up here, back in the original left side. Well, let's see. Secant theta is 1 over cosine theta. Cotangent is cosine theta over sine theta. And then I'd have to add that together, but I'd need a common denominator. So I'll have to take this one and multiply by sine theta over sine theta. And I'd have to take this one and multiply by cosine theta over cosine theta. So I'm just looking for common denominator here. Cosine theta over cosine theta. Okay, there it is. Then, what do we got? Push this together. This is sine theta. Push this together. It's cosine square theta. And we have a common denominator of sine theta times cosine theta. Yeah, cosine, sine. Okay, now, always keep in mind where you're going. We're trying to get to here. Sometimes there's hints, too. You see what the numerator has to transform to. The denominator must only have a sign in it. How are we doing so far? Well, our denominator has a sine and a cosine in it. Let's see. What could we do there? We could use the Pythagorean identity, perhaps, and rewrite cosine square as 1 minus sine square. And that's divided by sine theta times cosine theta. Not seeing how this will go to the original left side. So it could be there's a mistake. It could be we not yet seeing the correct way. That's why you practice these. So I'm going to go with my original over here, because that was awful short and sweet. So I like that. This one started to become a mess. And again, maybe it's because I'm not seeing the proper way. Maybe I'm leading you down the wrong path. Maybe there's a mistake. Or maybe this will work out just fine. We're not done yet, but this is getting lengthy on the right side. So I think we'll be satisfied with what we have right there. Separation of numerators. That's a very good technique to know. Okay. Now, before we do problem 5, let's go back to the PowerPoint and look at a more complicated example illustrated there. And then we'll come back and do problem 5. So over here in the PowerPoint, here's our identity that we have to verify. 1 over 1 plus sine theta plus 1 over 1 minus sine theta is equal to 2 plus 2 tangent square theta. It's a big beast. Okay. Hard to say which side's the more complicated, but you could say, well, which side do you see something that you know how to do? And, okay, we can convert that to sine square over cosine square. Sure. It's tangent sine over cosine, so tan square is sine square over cosine square. We could do that. Over here we have two fractions. Well, I could add it together with a common denominator. And that's the approach that's being taken right here. So we'll take 1 over 1 plus sine theta, and here it is, 1 over 1 plus sine theta, multiply top and bottom by the other denominator. Likewise, take this fraction and multiply top and bottom by the other denominator, so that the denominators are now the same. Okay? So the numerators then can be written down as addition, divided by the same common denominator. Okay, it gets us that far. Oh, and then negative sine theta and sine theta add to 0, and 1 plus 1 is 2. So the numerator simplifies. So now we got that far. Now what? Looking here. Well, we could multiply this out. 1 times 1, 1 times negative sine, sine times 1, and sine times negative sine square. And when we do that, this is now the result. Well, how are we going to make that into this? I will show you how to do that, but I'll show you what's going on here in the PowerPoint slide first. So the idea is, say this is you doing this and you're not sure how to connect the left side to the right side. There's no problem with starting again on the right side, 2 plus 2 tan square theta, manipulating this until we end up with what we had on the left side, and still, independently, we can show left and right side are same. That's the strategy being used here. It's a good strategy. It's sometimes tough to make one side completely into the other side. So let's replace tan square with sine square over cosine square, right? Since tangent sine over cosine, tan square is sine square over cosine square. So we'll replace that. There it is. And we now have two fractions we can add together with a common denominator. So we'll multiply the top and bottom here by cosine square. That's what's happening right there. This is just recopying down the second fraction again. We have the same denominator, so write it once. And now we have this expression. Okay. Now what? Well, to look at that, stare at that, think about that. Well, we have a common factor at 2. We could factor out a 2. And that's what's going to be done here in the next slide. Factor out a 2. Why do that? Well, because you can. Does it go anywhere? Turns out it does. Cosine square plus sine square is the Pythagorean identity. That's 1. 1 times 2 is 2. Now we have 2 over cosine square. Well, that's not what we had on the other side. But by the Pythagorean here, sine square plus cosine square is 1. As I showed you, solve for cosine square and you get 1 minus sine square. Replace this, 1 minus sine squared. This is what we ended up with by manipulating the left side. And that's what is being stated here on the last slide. When you start out with the original problem, left side, and manipulate, we got this. When you start out with the right side and manipulate it, you got the same thing. Therefore, the identity is verified because both sides are shown to be reducible to the same thing. So that proves equality. Okay, so before we end here, I'm going to take you back and show you a different way to handle this one right here. If you followed this part, taking the left side, simplifying it down to here, and how do we connect this to the right side? So let's see. Let's write down what we got. 2 over 1 minus sine square theta. Okay, what can we do with that? Well, by the Pythagorean identity, 1 minus sine squared theta is equal to cosine square theta. Okay? But 1 over cosine is secant. And 1 over cosine square would be secant square. So in other words, I'm thinking about this like this. 1 over cosine theta square. Right? This is how we write it. This is what it really means. And I'm separating that out. So 1 over cosine is secant, and so 1 over cosine square is secant square. This is 2 secant square x. Okay. Now what in the world are we going to do with that? Well, let's see. Pull up our fundamental identities here. Where are we here? Secant. Secant square is replaceable, equivalent to 1 plus tangent square. So I'm going to replace this with, replace secant square with 1 plus tangent square. Okay. Distribute the 2. 2 times 1 is 2, plus 2 times tangent square, and that's the right side. Check that, make sure. Yep, that's the right side. Show it equal to 2 plus 2 tangent square. So we got it by staying on the left side and ending up with the right side. So there's more than one way to go about it. Let's look at the last problem that we need to come back to here, number 5, and we'll verify that identity right there. What do we got here? We've got 2 fractions, so we got sine of x over 1 plus cosine x added to 1 plus cosine x over sine of x. Somehow that's equal to this small expression 2 cosecant x. Now if you start on the right side, true, this is 2 over sine of x, and then what? How are you going to blow that up to be this? Oh, and yes, there is a way to do that. It's not very obvious. So I think I'll start on the left side. What do I see? I see the addition of 2 fractions. Add those 2 fractions together with a common denominator. Okay, so we got sine of x over 1 plus cosine of x. We'll multiply that fraction by the other denominator. Okay, so this is just arithmetic here. Arithmetic is generally lengthy, but it's easy. And then, let's write that correctly. And then we'll multiply that by the other denominator, 1 plus cosine x over 1 plus cosine x. Okay. That's just to get it equal to a single fraction. So now our denominator is sine of x times 1 plus cosine of x. Right? We got the same thing twice. Numerators, sine times sine is sine squared. There's that one. Plus. Now I think we'll multiply this out. 1 times 1 is 1, 1 times cosine x is cosine x. Cosine x times 1 is another cosine x. And then finally, cos x times cos x is cosine square. Okay. So that's multiplying 1 plus cosine by itself. Okay, what does that reduce to? Well, we got sine square x plus, okay, we have 2 cosines right there, plus 1. 2 cosine of x plus cosine square x over our denominator. Okay, now, looky here, sine square x, make sure that's a plus sign, has to be a plus sign, plus cosine square x. So in other words, I'm just thinking of rearranging this to be sine square x plus cosine square x plus 1 plus 2 cosine x. So this is my rearrangement of my numerator right here. Okay. But you got to make sure that that's a plus sign. You can't just put 1 there. You have to make sure it is already in existence. Well, this is equal to 1. So my numerator here is 1, that's sine square plus cosine square, plus this 1 here, plus 2 cos x. Okay, all divided by our common denominator, sine of x times 1 plus cosine of x. Okay. And now 1 plus 1 is 2. Okay, so this is 2 plus 2 cosine of x over our denominator, sine of x times 1 plus cosine x. Look at that. Now what? Well, we could factor out a 2 since it's common to both terms. Factor out a 2, 1 plus cosine x over our common denominator. See how some of the moves are arithmetic and some of the moves are algebraic, and some of the moves are identities. It's what makes them challenging. And you're never quite sure what is next, so you try something and see where it goes. Most paths lead to dead ends, and some of the paths open up to be something worthwhile. Now, because we have multiplication, and only because of that, we can divide out those 2 terms right there, and we now have 2 over sine of x. And that's perfect, because division by sine of x means cosecant of x, right? This is, in other words, 2 times 1 over sine of x. Just thinking about the fraction differently. And that is 2 cosecant x. And why is that a good thing? That's what we were asked to show. So we've got it. So let's review that. Adding together by using a common denominator, adding together both fractions. Multiplying out those fractions, and then realizing that we can rearrange that a little bit. Don't have to rearrange it. I'm rearranging it just to show that that is the Pythagorean to be 1. Little addition right there, 1 and 1 is 2. Another algebraic move there, factoring out the 2's. I lost you here. Sine square and cosine square, so that's a 1. 1 and 1, 1 and 1, so that makes the 2. And then another arithmetic move there, factoring out the 2. And then a little more arithmetic, then a little bit of trig. It's a nice problem. Combinations, a little bit of everything. So I hope that helped out. So that's the conclusion of section 6.1 problems.